All right, Algebra 2, into Lesson 3. So we've been talking about exponents and then base 10 and scientific notation. Now let's talk about rational exponents. What are 2 raised to the 1/2 and 2 raised to the 1/3? What is the value of 2 raised to 1/2? Oh, I don't know if you're going to grab your calculator and start typing and see what happens. But 2 raised to the 1/2, yeah, you stuck with me? Let's try to evaluate. 1/2 is somewhere between 0, well, it's exactly halfway between 0 and 1. So 2 raised to the 0 power is 1. 2 raised to the first power is 2. So can we assume that 2 raised to the half power is 1.5? Okay, somewhere in between. Really, you could answer that anywhere, but that's one way to think about it. Let's graph some stuff. So graph your function f of x equals 2 to the x for every integer from -2 to 5. So let's do these. F of -2, f of -1, 0, 1, 2, oh goodness, 3, 4, oh goodness. So -2, that'd be like 2 to the -2, which is 1 over 2 to the 2, 1/4. 2 to the -1, 1/2. 2 to the 0, 2 to the first power, 2 to the second power, 2 to the third power, the fourth power, the fifth power, right? Or Miss Carly forgets how to multiply, and that's not proper writing. Oh, there we go. It wouldn't erase. All right, let's graph. So we had -2. You guys could probably do this better on your paper because you can get a little more accurate than my stylus. -1. If we look, the y-axis goes by 4s. 0, 1, 2, 3, 4, 5. Excuse me. Okay, there's our graph. So if we go back to the value of 2 raised to the half power, we have a graph that we can read now, right? It's somewhere in between here. Okay? Oh, it does say to connect your graph with a smooth curve. Good luck with that. Hey, that's not so bad. Very cool. Even though we did integers, which we never usually connect, but it did tell us to connect the points on your graph with a smooth curve. Random question. Since they told us to connect the points with a smooth curve, what does that tell us about the domain of this graph? It really isn't the integers between -2 to 5. It's really all the points. Between the integers, like all real numbers, right? And not even, it's all the points. So the domain of the function includes all the points between the integer points that we plotted, right? So how does this graph support or not support our answer to the first question? If we look, f of 0 and f of 1, so somewhere in between there will be our value of f, the 1/2. Okay, well, it's sort of hard to read. Where x equals 1/2, it looks like the value is somewhere between 1 and 2. The scaling on this graph probably isn't really detailed enough for me to find my answer. But that's okay. Let's try again. Let's see if we can graph it again. The graph on the right shows a close-up view for f of x equals 2 to the x for just this range, from x equals negative 0.5 to x equals 1.5. Find two consecutive integers that are under and over estimates of the value of 2 raised to the 1/2. We already have. We've done 2 to the 0 equals 2 to the 0 equals 1, and then 2 to the 1 equals 2, right? So we know that 2 to the 1/2 is somewhere between 1 and 2, somewhere in between there. Does it appear that 2 to the 1/2 is halfway between the integers you specified in exercise 1? Let's see, 2 to the 1/2 is drawing slowly. There. Ooh, I don't like that one. Right there. Okay. Not really. A little less. Right? So use the graph of f of x equals 2 to the x to estimate the value of 2 to the 1/2. I got about 1.4. About 1.4. Okay, use the graph of f of x equals 2 to the x to estimate the value of 2 to the 3rd. Ooh, 0.333, so 1, 2, 3, somewhere around there. So that'd be 1.5, 1.4, 1.3, about 1.25, roughly. It's a guesstimate. So let's think about this. What is the value of 2 to the 1/2? Okay, our initial guess was a little too big. Our second guess, which was from a graph, made it seem like about 1.4. So 2 to the 1/2 we think is about 1.4, right? How can we make a better guess? Well, the first graph that we did was too big. We couldn't guess it. So we got a more detailed graph with smaller increments, and we got much, much closer to the answer, right? So we could actually get closer and closer and closer to the answer if we got a better graph that was more detailed, more detailed, more detailed. But we're not going to do that. It's okay. Let's talk a little bit about how we can get to 2 to the 1/2, right? If you remember, we've done b to the m times b to the n equals b to the m plus n, right? So what do you think 2 to the 1/2 times 2 to the 1/2 is? 2 to the 1/2 plus 1/2 equals 2 to the 1, which is just 2, right? So let me take you on a little trip. Let's talk about squares. So what unique positive number can I square to get the answer 2? So what unique number can I square that will give me an answer of 2? Okay, what is the only positive number that when multiplied with itself equals 2? Okay, not much, except well, let's do that. Right? So the unique positive number that squares to 2, the square root of 2. So that's really all that we have. So we can really say here that this is the same as that, right? So both statements, this one and this one, involve multiplying a number by itself and getting 2 for an answer, right? So we know that, very important here, 2 raised to the 1/2 is the same as the square root of 2. Okay, that's what I was getting to. You were wondering where I was going. That's where I was going. So what about this? Okay. What am I doing? 2 to the 1/3 plus 1/3 plus 1/3 equals 2 to the 1 equals 2. Yep, that's the same as what we see here, the 3rd root of 2 times the 3rd root of 2 times the 3rd root of 2. Oh, gosh. Sorry. Equals 2. If I have 3, 1, that's supposed to be a 1, 1, 2, 3 of a 3rd root, I get 2. I could actually, up here, I can say that 2 to the 1/3 plus 1/3 plus 1/3 is the same as 2 to the 3/3, which is equal to 2 to the 1, which is equal to 2. Okay, that means that down here, I can say the 3rd root of 2 times the 3rd root of 2 times the 3rd root of 2 equals the 3rd root of 8. Well, 8 is 2 times 2 times 2. Pretty cool, I hope. All right, let's write down a rule for what we're doing, okay? We just said that 2 to the 1/2 is equal to the square root of 2. I should say that we never write that 2 there. If that 2 is missing, we assume that it's a square root. Something raised to the 3rd power is the same as the 3rd root. Therefore, guess what the rule is? Something raised to the 1 over n power is the nth root, right? Makes sense. How about 2 to the 4th power? Yep, that's the 4th root, right? 2 to the 10th power is the 10th root. We could go on and on and on, but who wants to do that, right? If we did 2 to the 1 over n to the nth power, that's the same as 2 to the 1 over n, 2 to the 1 over n. Ooh, I don't know why I wrote that. 2 to the 1 over n, and I can do that n times. That means as many times as I feel like it. But that also equals 2 to the 1 over n plus 1 over n plus 1 over n dot 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 n times, which gives me, if I do that n times, 1 over n plus 1 over n plus 1 over n times is 1, right? Remember what we do here? When I have an example, x to the a raised to the b, I multiply them. That's what we do here. 2 to the 1 over n raised to the n gives me 2 to the 1 over n times n, which is 1. Duh. Awesome. All right. Okay, let's try some examples. So, what is the 4th root of 16? So we can say that x to the 4th equals 16. Therefore, x equals 2. Right? Because 2 raised to the 4th power is 16. So the 4th root of 16 equals 2. Okay, we're just playing a little bit of mind games right here. It's all right. What is the cube root of 125? So x to the third equals 125 when x equals 5, because 5 raised to the third power equals 125. Therefore, the cubed root of 125 equals 5. What is the fifth root of 100,000? So x to the fifth equals 100,000 when x equals 10. Okay, a clue here with that one. I have 1, 2, 3, 4, 5 zeros. That means it's 10 raised to the fifth power. Because 10 raised to the fifth power equals 100,000. Therefore, the fifth root of 100,000 equals 10. Okay? All right, let's see how you do. Try these. Okay? Fourth root of 81, you may need to think to yourself, like 2 times 2 times 2 times 2, that's 4 2s, is not 81. How about 3 times 3 times 3 times 3? Yep. So the root is 3. Okay, what times what will give you 32? Like, you have to multiply it 5 times. Ooh, tricky. Well, if I have the third root of 9 and the third root of 3, that really is the third root of 27, which gives me 3. Remember, if they have the same power, the same root, you can multiply what's underneath them. This is just like nth root of a times the nth root of b equals the nth root of ab. Okay, same here. I have the fourth root of all this stuff. 25 times 100 times 4. I'm being lazy. I apologize. That gives me 10,000. And remember, 4 zeros means it's 10 to the fourth power. Cool. Awesome. I threw a negative out there. Okay? Can we take roots of negatives? We've talked about imaginary numbers, but with this one we can, because if I have a negative, and this right here is odd, it actually works. Negative 2 times negative 2, negative 2, that's 3, 4, 5. Okay, I've got positive 4 times negative 2 gives me negative 8, times negative 2 gives me positive 16, times negative 2 gives me negative 32. Just throwing that one out there for you. You may need it, right? But this one doesn't work, okay? Because it's an even number and a negative. So negative 2, 3, 4. Okay, here we have positive 4 times negative 2 is negative 8 times negative 2 is positive 16. I can't get that negative there with an even power, right? Here's a fun question. If 2 to the 1/2 equals the square root of 2 and 2 to the 1/3 equals the cube root of 2, what does 2 to the 3/4 equal? If we look at this one, I have 2 to the 1/2 is equal to, I'm going to put this 2 in the square root. Does that go there? If 2 to the 1/3 equals the cubed root of 2, does that go there? Well, let's try it. 2 to the 3/4 equals the fourth root of 2 to the third power. That's sort of cool. 2 to the third power is 8. I don't have a fourth root of 8 though, so that doesn't really help. But let's look at it this way too. Let's look at it a different way. 2 to the 3/4 is the same as 2 to the 1/4 times 3, right? Or the fourth root of 2 to the third power. It works. It's the same, okay? Since the properties of exponents and the meaning of an exponent made sense with integers, it does for these rational numbers also, okay? It works for everything. It's sort of cool. I could also write this as 2 to the third power raised to the 1/4. Same thing. 4th root of 2 to the third power. Pretty cool, huh? I love math. Can we try this one? 2 to the 3/4 power raised to the 4th. Ho-ho! That equals, let's just mess with it, 2 to the 3/4 power, 2 to the 3/4 power, 2 to the 3/4 power. Sort of fun, right? Or 2 to the 4 times 3/4, which is the same as 3/4 plus 3/4 plus 3/4 plus 3/4. It's like adding is the same as grouping, multiplication, right? Blowing your mind yet? Sort of fun. So 4 times 3/4 is the same as third power. 4 times 3/4 equals 3 equals 8. Mind-blowing, right? Sort of fun. All right. So let's just generalize. I'm going to give you just a rule. Oops, that didn't work. My pen. Just a random 2 to the m over n is the same as the nth root of 2 to the m, okay? Which is the same as the nth root of 2 to the m. It doesn't matter, okay? All right. Let's try some more exercises. Rewrite each exponential expression as a radical expression. So 3 to the 1/2 is the same as the square root of 3. 5th root of 11. Ooh, this one's sort of fun. I can say it is the 5th root of 1 over 4, which is the same as the 5th root of 1 over the 5th root of 4, which is the same as 1 over the 5th root of 4. Cool, huh? 6 raised to the 1/10, 10th root of 6. Cool. Rewrite the following exponential expressions as equivalent radical expressions. If the number is rational, write it without radicals or exponents, okay? So this first one, 6. I have 2 to the 3/2. It's the same as the square root of 2 to the third power, which is the square root of 8, which is the same as 4 times 2, which is 2 roots of 2. A little bit more work with these. 4 to the 5/2 is the square root of 4 to the 5th power, which is the square root of 4, all of it to the 5th power. And think of that. For every 2 square roots of 4, I can get rid of the root. I'm really going to write all 5 of them, aren't I? So this gives me 4, and that gives me 4, and that poor guy is lonely. 16 square root of 4. Did anyone see what I missed yet? What's the square root of 4? 2. Haha. So now we have the third root of 1/8 to the 5th power, which really gives us the third root of 1/8, the whole thing to the 5th power, which is easier to calculate because the third root of 1/8 is 1/2. raise that to the 5th power, and I get 1 over 32. Another one, show why the following statement is true. So we've learned a lot of rules. We know that x to the n is the same as 1 over x to the negative n, or x to the negative n is 1 over x to the n. Okay, that's why that statement is true, because of that rule. So rewrite the following exponential expressions as equivalent radical expressions. If the number is rational, write it without radicals or exponents. I'm going to push pause on this and work through these. The video is already pretty long, and I'd like you to practice these. You just don't have to watch me practice them. There you go. Check your answers. Okay. And the closing is a summary of the rules we've gone over, what the nth root of a number means, principal nth root of a number. We sort of skimmed over, I guess I skimmed over it. Principal nth root of b is the real nth root that has the same sign as b and is denoted by the radical symbol b. So the principal root of b is it's a real number. It's all of our perfect squares, principal roots. Okay? The nth root of 0 is 0. We always talk about that. What about the square root of 0? Well, it's 0. But that's it for today. Good job.